I haven't gone in my 3 years here. I never went. It's not sad. My girlfriend's like, we got to go. It's free. I'm like, yo, I'll just buy us tickets. Like, it's okay. Everything will be okay. I'm like, I'll go work all day Sunday, and I'll work 39 hours next week, and then I'll just buy us tickets, and we'll be fine. And because I'd rather just go on like a random Tuesday where it's just like old people and like families with little kids, and then.
It's always.
Yeah, I know, right? That's why I've never ended up going. See, Sunday mornings I'm not up. I'm asleep. I'm like half asleep right now. This is just like me like chugging a Red Bull, and like I'm kind of awake right now. So what's up? They have to come. So, but you got it working. Streaming. Hey, what's up, everyone? All right. So I might just start on the whiteboard and start yelling. Okay. Just because, so I can get started. Oh yeah, put it right in front of me. Yeah, that's fine.
You want the other one next to you?
No, I'll just work off one. All right, guys, so I'm going to start on the whiteboard. I'll talk as loud as possible, so if you can't see it, at least, thank you for the smiley face. So that as long as, if you have it in front of you, you'll have an idea. I'll repeat myself as many times as I need to until the people show up. They're on their way. They're going to turn on the projectors. It'll take like 48 seconds to warm up, and then they'll finally turn on, and then everything will get better. But for right now, we should start, right? We're not just going to sit around and keep waiting for them. Awesome. Are you from the union? Oh, no. Let's say you just look so official, bro. Like, I don't know. You threw me off. All right. So we're starting from chapter 7. And the first question is calculate the wavelength. So this is where you guys are like, oh, my God, these problems. I remember them. Calculate the wavelength of a red light emitted by a barcode scanner that has a frequency of 400. What's happening? Everything's a mess, guys. I'm sorry. I'm going to pretend like I know how to work this thing.
You gotta do both. Yeah, you gotta do both.
All right, cool. All right, there we go. Okay, so try to write big, too. So this problem gives us the frequency. They say it's 4.62 times 10 to the 14th seconds inverse. And what's another way that we could see that unit? Yeah, we can see it as hertz, and we can see it as 1 over seconds. So it's just like different ways that you can be shown it. And I mean, you got to know it all sorts of ways. You could see it different ways throughout the exam and whatnot. But yeah, and so it wants us to calculate the wavelength. So what is the equation that we're going to be using here? Does anyone know? What was it? C over V equals wavelength. And yeah, that's what we need. And remember that he's going to give you some of these constants on the exam. I think he's going to give you all of them, right? So C is just 3.00 times 10 to the 8th meters per second. And our frequency is this number. So we're just going to take that, and we're going to put 4.62 times 10 to the 14th. It's like 1 over seconds, right? And so the reason you want to be able to see it as 1 over seconds is because we're going to cancel these two out, and we're left with meters, pretty much. And that's the unit we need for wavelength. So if we grab our calculators and we solve this out, are you turning on the projectors? All right, thank you so much. So one thing that I saw a lot of people make mistakes as we went through the semester with this, don't know how to do the problem and get it wrong because you put in your calculator wrong. Remember, anytime you do like you get scientific notation or whatever, just put parentheses around it because your computer, you guys are smarter than your calculator. Your calculator is just like numbers and it computes. So you got to tell it what to do sometimes. And then so you should get this horribly small number. You should get 6.49 times 10 to the negative 7th meters. But wavelength is usually in what sort of unit? Nanometers, right? And so if we convert this to nanometers, it'll be 649 nanometers. Yeah, I'm sorry. We're getting the projectors turned on right now, so this will only be horrible for another like 2 minutes. But so pretty much, what's up? Nanometers, so that's a good question. I'm going to erase this so we can see it. The conversion from meters to nanometers is in 1 meter, you have 10 to the 9 nanometers. So pretty much this is 10 to the negative 7, so once the 7 goes away, you would move over 2 more times. It's something that if you practice it enough, you just understand. So if you have like 6.49 times 10 to the negative 7, when you put it in nanometers, it'll just be 649. And that works both ways. And you usually end up with that sort of power when you're doing these problems because, if you guys remember the electromagnetic spectrum, it's all like hundreds values. So yeah. Any questions? This is easy stuff, simple equation. And the way I would think about it is, am I going to get this equation on the exam? If he gave it to you on the Chapter 7 exam, you'll probably get it on the final. If he didn't, you probably won't. But hope for the best and prepare for the worst, right? Is that how that goes? I don't know. Oh. My thing is over here. Okay. This is kind of horrible because it's not working. I love my job. All right, so the next question is a nitrogen gas laser pulse with a wavelength of 337 nanometers contains 3.83 millijoules of energy. How many photons does it contain? So let's work on that. All right, so we know that it has a wavelength of 337 nanometers. I'm going to do this. What happened? Keep moving them that way. All right. Look how strong I am, everyone. I don't need to go to the gym. What's going on? Are they working? Oh, they're turning on. Everyone, yes. The projectors are turning on. Woo! All right, cool. So forget these whiteboards. Everyone hates them. I hate them. Okay. So you guys can see my beautiful face? Well, some of you can. All right. So that one's working. Let me zoom in a little bit. Much better, right? No one's cranky anymore. I'm not cranky anymore. All right. Okay, so this is probably like one of the harder ones from this chapter in terms of math. And so I wasn't able to cover all the concepts, but make sure you understand stuff like constructive interference, destructive interference. All that stuff will be important. He can ask concept questions about anything from chapter 7 to chapter 10. I mean, even if you're not in Dr. Hernandez's class, your professors will ask you concept questions. That's how you understand the math. That's how you know what's going on. So make sure you don't have to go read all 4 chapters. If you have time like that, go ahead. But just skim through. There's those summaries at the end of most of the sections that are just labeled by bullet points, and you're going to want to at least read those. But as you guys saw, even during the course, when you were just studying one chapter, he still got you with some really detailed concept questions, and he's hoping that you either remembered them or went back and learned them and stuff like that. So this review is focused more on the math aspect of it, and if something about the concept comes up, I mean, we'll talk about it, but for the most part, we're dealing with math because that's the hard stuff, I guess. Okay, so we have right here, this is our E pulse, right? And this is our wavelength. So it's labeled by lambda. Now, a few of the equations we need is going to be, energy. The energy relation between wavelength is E equals hc over lambda. And like I said, if he didn't give this to you on the chapter 7 exam, you're going to have to memorize them. You're going to have them in your back pocket, and you'll have to take them out and use them when necessary. Another equation we need, so something really important is what kind of energy is this? And that's what kind of makes this question like, and some of you guys might be thinking, oh, we have energy and wavelength, and we have 2 constants, so we're not really solving for anything. But this is energy of the photon, right? And what we have is energy of the pulse. And so when we get energy of the photon, we're going to use this equation right here. Energy of the pulse over energy of the photon equals number of photons. And for some reason, if I go off the screen, you guys got to yell at me because I'm going to be trying to go quick because we lost some time in the beginning. So pretty much, the first thing we do is we convert this into meters, right? Because that's the only way we can plug it in. And like I said, like we did with the problem before, it's that simple conversion. When you have 100 nanometers, it's really, I'll show you. It's 3.37 times 10 to the negative 7 meters. And if you studied a lot during this chapter, you get this. You understand why that happens. And then so pretty much we plug everything into this equation right here. And what we get is H, which is 6.626 times 10 to the negative 34. And we get 3.00 times 10 to the 8th. Yeah. And we put that all over this. Thank you, sir. Yeah, that's just watermelon juice, guys. I needed to eat some breakfast this morning. It's not blood or anything. I don't know why I said that. All right, cool. And then what we get from that is 5.89 times 10 to the negative 19 joules. So that's a good question. So Molly asked, why do we convert this to meters when wavelength is usually nanometers? So if we look at the units right here, so I'm going to do a unit conversion up here, just like the math of the units. So that's Planck's constant. This is speed of light. And we want to be left with joules, right? Because we're talking about energy. Now, this is seconds on top, that's seconds on bottom. They cancel out. And so what we're left with is joules times meters, pretty much. And we want to get rid of meters, so we have to have meters down here, and we'll be left with joules. So that's how you have to do it. That's a good question. All right. What's up?
The number on the bottom is, isn't it H? The equation is that?
Yeah, so the equation is hc. So this is Planck's constant, this is speed of light, and then down here we have lambda, which is wavelength. And up here we had it in nanometers, and we converted it to meters, and then we plugged it in. And then we're left with joules. And so the next thing we're going to do is we're going to convert our E pulse into joules, because we want joules to cancel out. We want to be left with number of, and the units for numbers is just like the number itself. So when we convert that from millijoules to joules, we'll get 3.83 times 10 to the negative 3 joules. And then that's our E pulse. We want to divide that by our E photon. And what we're left with is 6.49 times 10 to the 15 photons. So the reason this is considered hard is just because there's like a longer process to it than some of the other questions. But any questions about this? All right, cool. So I'm going to move on. All right. So this question is asking you to arrange the types of electromagnetic radiation, visible light, X-rays, and microwaves in order of increasing wavelength, frequency, and energy of a photon. And so pretty much for wavelength, so I'm going to start with energy of a photon, because when we look at the electromagnetic spectrum, it's in terms of energy. And you want to think of everything as energy first, and then relate it to frequency, and then relate it to wavelength. So to start with energy, which one of these is the lowest energy? Microwaves, right? And visible light, like literally everything, all the colors you're seeing, science, woo. And then X-rays, obviously. Now, someone might be thinking in their head like, oh my God, I got to go memorize the whole visible spectrum. It's pretty intuitive. We use X-rays every single day, and they don't really, oh, no we don't. We use microwaves like pretty much every single day. All of you that live in a dorm, you have a microwave. That's how you guys eat dinner most of the nights. Some of you are like, no, not me. But yeah, so we use them a lot, and they don't really harm us. Visible light, you know, visible light is a little bit more dangerous. And then X-rays are obviously the very most dangerous. You got to throw that lead jacket on every time you get one so you can have kids if you want them when you grow up. So yeah, and so like we said, we think about it in energy, and then we're going to relate it to frequency, and we're going to relate it to wavelength. Now pretty much, how is energy and frequency related? Is it directly proportional or is it indirectly proportional? It's directly proportional. So it should be the same as C. And then we think of wavelength. Is energy directly proportional, indirectly proportional to wavelength? It's indirectly proportional. So it should be the opposite, where X-rays have the shortest wavelength, and then visible light, and then microwaves. And if that confuses you guys for any reason, we just go back to the equation that we were looking at up top. And, yeah, I'll probably do this different. And then we have E equals HV. So if you look up here, as this number gets bigger, energy should get bigger. So let's just say this constant is 1. If you do 1 times 2, it's 2. If you do 1 times 4, it's 4. So as frequency gets larger, energy gets larger. But it's different for wavelength. If we give both of these 1 just because they are constants, they don't really affect it in this sense. When this number is 1, the answer is 1. When it's 2, it's 0.5. When it's 4, it's 0.25. So as wavelength gets larger, energy gets smaller, meaning it's indirectly proportional. So the way I like it is you should think of energy first and then relate it to the other answers. Any questions? All right. I added this one last night because I was looking at it, or not last night, but when I made the review. And this is about photoelectric effect, which there was a lot of confusion about it when we were learning about it, because Dr. Hernandez is a scientist, and he will talk science to you when he talks about this, and that kind of confuses us sometimes. because we're not scientists yet. So pretty much we get 3 wavelengths. And we observe 3 different things. Observation A is there's no photoelectrons observed. Observation B is we have photoelectrons with a high kinetic energy relative to observation C, where we have photoelectrons with a low kinetic energy. Now, if you guys remember, the thing that determines the photoelectric effect is a threshold frequency, right? We need to hit a certain frequency, and then we start seeing photons emitted. So, like we just talked about, is it going to be a small wavelength or a large wavelength that gives us a high energy? Small wavelength, right? Yeah, small wavelength gives us a high energy, and if we have high energy, we have high frequency. And that's kind of how you want to think about it. This chapter is all about understanding the relationship between energy, frequency, and wavelength. And so we're going to get the lowest energy, the largest wavelength, is going to give us no observation, right? Can we all agree with that? So this is going to be the 632 nanometers. And then when we're picking between these two, we should see a higher kinetic energy, a higher frequency with the smaller wavelength, right? So we can say that this one is the 325 nanometers, and this one is the 455 nanometers. Any questions?
Yes.
What's up? What's up?
Why again? Why is each,
Because we're trying to hit a specific threshold frequency. And if we use a relationship that a small wavelength will give us a large energy, which will give us a high frequency.
I get, but I don't understand why B and C are the way they are.
Because of what I was just explaining to you. So if you get it, I'm not sure. It's just like we have a higher kinetic energy for the higher energy, the higher frequency wavelength. That's all it is. There's not much more to it. So if you're trying to think it beyond that, you're just overthinking it. All right, cool. All right, so right here we have calculate the wavelength of an electron traveling with the speed of 2.65 times 10 to the 6 meters per second. This is a de Broglie wavelength equation problem. Now what you guys might have noticed is that in the test it says de Broglie wavelength in the problem. And so people are asking me, what's the difference between a chapter 7 question and a final exam question? In the final exam, he just won't put de Broglie's wavelength. You'll just have to know that that's what's going on. And yeah. And so you guys might be like, what the heck? And that's just how it is. So the way we set this up, the equation, so that it equals wavelength, is we would have lambda equals h over mv. And now there's 2 equations in this whole chapter where v does not mean frequency. It actually means velocity. And those are the 2 equations that were named after people. That's de Broglie's wavelength and Heisenberg's uncertainty principle. So that's how I remembered it. The people who had names, they just did it differently. So pretty much, we're going to plug in h as 6.626 times 10 to the negative 34. We're going to plug in mass as 9.11 times 10 to the negative 31 kilograms, right? And that's the mass of an electron. All right, so what you need to be careful about is he will probably give this to you on the exam. I don't remember it, and I try to prepare everyone who came to SI for this. He will put it on your exam as the mass in grams. But we can't use grams here, right? Because if we break down joules, it's kilograms times meters squared over seconds squared. So if you use grams, you're going to get the wrong answer. And that's pretty much what he wants you to know about this. He's going to give you the equation, and he's going to give you pretty much all the concepts. All the, what are they called? Constants, yes. He'll give you the constants, and then he'll give you velocity. So pretty much you're just plugging stuff in, but it's how do I plug it in? Why should it be kilograms and not grams? And that's the difficult part about this question. So remember, Dr. Hernandez doesn't like to trick you guys, and I'm going to get some laughs. He doesn't like to trick you guys. He likes to challenge you guys. That's the way we look at it when we sit down and talk about it. We're challenging you. So the idea is, do you really know this, or are you going to look at the equation on the back page and just plug stuff in and be like, I got it right because I didn't know what I was doing, but I just plugged everything in. And then so we'll plug in 2.65 times 10 to the 6th And then from this point, it is what I like to call a calculator problem. And remember, just put parentheses around everything. And what you should get is 2.74 times 10 to the negative 10 meters. And so for this question, all the answer choices would be in meters. If they were in nanometers, you would just convert. For 1 meter, you have 10 to the 9 nanometers. You do that conversion, and then you're good. You got the answer either way. Any questions? What's up, man? Can you say that just a little bit louder? All right, so that's a good question. It actually, we put it in kilograms in the equation because it'll get canceled out. It'll get taken care of. So just to show you, when we break down joules, so you know Planck's constant is joules per second. And when we break that down, we get kilojoules times meters squared over second squared times seconds. And that gets put over kilograms and meters over seconds. So what happens is this seconds cancels out with that seconds, this one cancels out with that one, this meters cancels out with that meters, kilograms cancels out with kilograms, and we're left with what we want. So you plug it in as kilograms, and then the problem will take care of it. And go Real Madrid. Are you going to watch El Clasico today? Absolutely. All right. Any more questions about that? That was a good question because, like I said, that's the whole understanding. That's what's going to be hard about this question is plugging in kilograms or grams, and he'll most likely give it to you in grams. So, because remember, Dr. Hernandez will challenge you guys, not trick you guys. There's a big difference. All right, so quantum numbers. It's just pretty much the most difficult way to ask quantum numbers is to make you do pretty much everything and understand the idea of what's going on. So what are the quantum numbers and names for the orbitals in an n equals 4 principal level? So if n equals 4, what are our possible L values? Yeah, L would equal 3, 2, 1, and 0. And so pretty much what we're going to do here is now that we figured that out, we make sort of like a chart. So when L is 0, when L is 1, when L is 2, when L is 3. And then we want to know what the possible ML values are. And so what's a general equation that we should know for ML values related to L values? Yes, plus like positive L to negative L going through 0. That's very important. So if L equals 0, the only possible ML value is 0. If L equals 1, it can be negative 1, 0, and positive 1. And then this will just repeat. And it'll repeat again. And then so we have to ask ourselves, when L equals 0, what kind of orbital are we dealing with? S. And what's our principal quantum number? 4. So this is a 4s orbital. When L equals 1, what kind of orbital? When L equals 2? And when L equals 3? What about when L equals 4? It might be possible. No, but we don't need to know it. And actually, I don't think it's possible, so I was messing with you. But yeah, just don't let him ask you questions like that and throw you off. Now remember, if he asks you to pick from a set of quantum numbers, which one of these is incorrect, he doesn't have to be realistic. He can say n equals 6, L equals 5, and that would be correct. He's just trying to test your understanding of that concept, that when you have n, L is n minus 1 to 0, ML is positive L to negative L going through 0. And so that's what he's trying to test there, that general idea of quantum numbers. And so these are all the quantum numbers of a 4s, like in the 4s principal energy level. Now another question was how many total orbitals were there? So you can do one thing where you just count up all your MLs, right? And if we counted this, we would get 16. So the answer to that question is 16. Now another way we could do this is we could do L, like 2L plus 1. And so pretty much, what's 2 times 0 plus 1? It's 1. 2 times 1 plus 1, it would be 3. And so that's pretty much what's happening. But if you did that, you would have to add them up. Like you would have to do it for this, 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 and this, and then you have to add up all those numbers. And you would get 16 again. And now another way that only works in this situation is that you can do n squared.
Wait, why does it only work?
Why does it only work in this situation? Because Dr. Hernandez on the test, the book, is asking for how many n equals 4 orbitals. So they're asking for how many orbitals in n equals 4, the whole thing. So you can do n squared, and you'll get 16, obviously. Now a different question that you can get asked, and this is how the book always asks you like this, and on the test he always asks you the other way. If you remember on the test, well here, let me pull out the exam. So look, if we look right here, can everyone see that? What is the total number of orbitals having n equals 4 and L equals 0? So he specifies a specific sublevel. He wants to know L equals 0. So you can do 2L plus 1, and then you would get 1. Not trying to throw whoever this test is under the bus, but they did n squared, and they got 16. And so they ended up with the wrong answer, and that's because he doesn't want to know just n equals 4. He wants to know n equals 4, L equals 0. So on the exam, another way this can be asked, which is another way the book asks it, they ask, I'm going to do it up here. What are all the quantum numbers associated with 5D orbitals? And how many 5D orbitals exist? So to get this right, you would have to break down what 5D is. And so when we have 5D, what's our n value? 5. So n equals 5. What's our L value? I think I heard 2. And then ML can be either -2, -1, 0, +1, or +2. And then MS, what are the only two values for MS? +1/2, -1/2. So that's how that would work. But pretty much we're specifying L equals 2. So we could do 2L plus 1, and we would get 5. So those are a few ways you could see it. Any questions? What's up?
What was the 5 part? The last part. The very last part.
Right here?
No, the very, very last part you just said.
Yeah, so I'm sorry. So another way we can find how many orbitals exist in a sublevel is we can do 2L plus 1. And so that would be 2, our L is 2 in this case, plus 1, and that would equal 5.
When they asked for orbitals, they just talking about ML.
Pretty much. Because remember, ML is the different orientations of the orbital, so that's how many orbitals you have in an L level. Any questions? How do we know L equals 2? And that's because we see D, and we know when our orbital is D, our L equals 2, just kind of like what we did down here. So when L equals 2, everyone told me D. So if it said 5F, L would equal 3 in that case, kind of thing. So you want to be able to work those in both directions. Any more questions? Okay, cool. All right, so here's the kind of question I was talking about. Which set of quantum numbers is erroneous, which means it just doesn't work, and why? So if n equals 3, can L equal 0? Can ML can only be 0. So this one's correct. If n equals 2, can L be 1? And ML can also be -1, right? If n equals 1 and can L equal 0? That's all it can equal. And ML can only equal 0. And then right here we have n equals 4, L equals 1. But if L equals 1, can ML be -2? No, so this is the correct answer. All right, moving on. So this question says, determine the wavelength of light emitted when an electron in a hydrogen atom makes a transition from an orbital in n equals 6 to an orbital in n equals 5. So this might probably be like the hardest one for you guys to do because there's a lot of equations and there's a really important relationship in this problem. So some of the equations that we have to use is, well, to find the difference in energy, we would have to do final minus initial, right? So that'd be the energy of level 5 minus the energy of level 6. Another equation we need is we're going to need that relationship between energy and wavelength, so that when we find this energy over here, we can plug it in right here, and we can get wavelength. But these two energies are different, right? From what I said earlier, what kind of energy is this one right here? Energy of a photon, right? But what kind of energy is this going to give us? It's going to give us, yeah, the energy of the atom. So we have a really important thing going on right here. Energy of the atom equals negative energy of the photon. All right, so now that we have all our equations and whatnot, let's work out the problem. Oh no. What happened? Okay. Oh my God. Okay, so pretty much solving this equation up here, we're going to do negative 2.18. This is like Schrodinger's constant or someone's constant. I don't know. Someone got famous off this number. And it's 1 over n squared. So it'd be 1 over n final squared minus the constant again over 1 over n initial squared. And so let me write it out so you guys aren't like, what is this crazy man saying? All right, so that's what I meant. This was our n final, and this was our n initial. And so pretty much in this case, you can condense this, and you can say it's negative 2.18 times 10 to the negative 18, 1 over 5 squared minus 1 over 6 squared. And then pretty much what this will turn into is 1 over 25 minus 1 over 36, right? And once you do that math and you subtract them, and then you multiply that number times negative 2.18 times 10 to the negative 18, you will get negative 2.6644 times 10 to the negative 20 joules. But like we said, this is going to be our energy of the atom. So to make it energy of the photon, we have to throw a negative sign in front of it. So minus and minus will become positive. And then at that point, we can plug it in to this equation up here, because now this is our energy of photon. We can plug it in up here, and it'll be HC. I'm not going to keep writing out these constants. You guys know what they are. Divided by that number. And when you do that, you should get 7.46 times 10 to the negative 6 meters, which would convert to 7,460 nanometers. Any questions? All right, one thing that you want to know as far as the concept goes for a hydrogen atom, since this is a problem about a hydrogen atom, is that hydrogen are like, what's the word? It's degenerate, right? Hydrogen's atom degenerate, because what we see is we see n equals 1, n equals 2, 3, 4, 5, 6. We see it go up in that very standard like fashion. But what's the largest jump? 1 to 2? What's the largest jump? You guys are confusing me. Let me look this up. I'm pretty sure it's 0 to 1. It's going to be the largest jump, right? Yeah. Oh, no. So you guys are right. I'm sorry. It's 1 to 2 because it starts at 1. I apologize. So, yeah, 1 to 2 is the largest jump. And then when we go to 2 to 3, it's like 25% of that, and it gets smaller and smaller. And it's so small after 5 that it just says n equals 5 to n equals infinity, because it's like so small that they couldn't record it on the book. So As the principal energy level goes up, your jumps get smaller. Yeah. And so he could ask you a question, which transition results in an emitted light with the shortest wavelength? And shortest wavelength means what? Highest energy. So we'd be looking for the largest jump, like the largest gap or the smallest gap? The largest gap. So it would be the emission from the two lowest levels. So for example, 3 to 2 as opposed to 5 to 4. All right, cool. So that's, I'm going to do one more problem from chapter 7. And it's this one right here. What is the probability density in the radial distribution function for a 2p and a 3s orbital at the corresponding nodes? What is at a node? Nothing. So it's 0. You'll never find anything at a node. Me after this semester, just imagine I'm in a node. You'll never see me again. No, I'm kidding. But yeah, that's how it works. And there wasn't a question I could find on that, and he tested on it. And I think most of you were like caught off guard by that, so I wanted to talk about it. Okay, moving on to chapter 8. We have a few, so we just talked about degeneracy, and which kind of atom is it recognized in or seen in, and that's a hydrogen atom. Jesus Christ. We have Pauli exclusions principle, so do you guys know what that is? No?
Yeah.
What is it?
No two electrons have the same 4 quantum numbers.
Yes, very correct. No two electrons in an atom can have the same 4 quantum numbers, because then you would be talking about the same electron. So something else is Aufbau's principle, and one of the ways you were taught it is that rain method. Another way I talked to you guys about it is just the periodic table set up in Aufbau's principle. So if you went to my SI sessions or whatnot, you know what I'm talking about. And then Hund's rule, which means that you have to fill up the boxes one at a time before you can pair electrons up. And the way I think about that is everybody gets first before anyone gets seconds. And so every box should get 1 slice of pizza before another box can have 2 slices of pizza. And it's always made sense to me that way. So, what happened? That was Hund's rule, yeah. Hund's was really picky about how everyone ate. All right, so Coulomb's law. There's going to be a few charts that you want to go back and understand, and one of them will be Coulomb's law, because it's very odd, it's very confusing, but I was talking to someone yesterday about it, and there's a big difference between positive potential energy, no potential energy, and negative potential energy. And which one is more preferable? Negative, right? You want to have the lowest amount of potential energy, and negative is lower than 0. But for oppositely charged particles, you can go negative. For like charged particles, the lowest they can go is like a really small positive number. So you're going to want to take an extra look at that chart and just make sure you understand it. All right, so according to Coulomb's law, what happens to the potential energy of 2 oppositely charged particles as they get closer together? When I think of Coulomb's law, I think of magnets. And so 2 opposite poles of magnets, would they want to come together or be separated? They want to come together, which means they're at rest, they're at happy when they're close to each other, which means they will have, their potential energy would decrease as they get closer together. Any questions? So what are the 4 quantum numbers for each of the 2 electrons in a 4s orbital? So we already talked about this. If we have 4s, what's our n? What's our L? If it's s, our L is 0. What is our only possible ml value? But this is where it's different. We're going to have an ms for one electron and an ms for the other electron. And so the first electron is going to have an ms of what? Plus 1/2. And the second electron will have negative 1/2. And that's pretty much, this one is going to spin up, and this one's going to spin down. All right, cool. Okay, electron configuration and orbital diagram and determine the amount of valence electrons. So for magnesium, at this point, this is like really easy for you guys because you can determine valence electrons without even doing this, right? We've been using our periodic table to find valence electrons a lot. So I'm just going to do the short electron configuration. And so for magnesium, it's going to be neon 3s2, right? Everyone agree with that? And then I don't have a periodic table on me, so can someone just tell me what it would be for silicon? Silicone? Neon? Okay. Three S2, 3P2. Yeah, this is right below carbon, right? Okay, cool. And so how many valence electrons would be in magnesium? Yeah, we just find the highest principal energy level and we count the numbers on top. So we'd have 2 valence. And then what about for silicon? Yeah, this is a 2, guys. Yeah, it'd be 4 valence electrons. Okay. Sketch a periodic table and the trends. So I'm not going to draw the periodic table, but pretty much we have 2 arrows. We have one going this way and one going that way. So I probably should have done this in different colors. But for the arrow that's going down, and these are both increasing arrows. This is how I like to think of it. They're increasing in that fashion. So for this arrow, what 2 trends are increasing as we move down and to the left? Atomic, radii, and what else? Awesome, metallic character. Metallic, yeah. And then for this arrow, what 2 trends are increasing as we go up and to the right? Ionization energy. Be careful with electron affinity. That is a very general trend. It's very general, and we actually can't put an arrow to it. Putting an arrow to it will kind of mess you up. So just be very careful with that. I would actually go check the book and just read. It's like literally, it's one of those summary bullet points. I would just read that, and it tells you that there's a very general trend in electron affinity, but it's not strong enough for us to put like an arrow to it and stick to it every time. And if you go in Dr. Hernandez's slides, it says the same thing. It's a very general trend. But we're not like, no one got famous off that trend because they're like, you're wrong. So ionization energy and what else? What? Electronegativity, right? Electronegativity. Was there another one? No. All right. Yeah, and so this one's from chapter 9, and so we learned it a little bit later. But yeah. And I've been getting a lot of questions about, are we going to get the values on the final exam for electronegativities? I don't know because I don't write your final. I don't even make it at all whatsoever. But I would assume that you will not. Only because it's the final exam. You guys are about to go to Chem 2, organic chemistry, and at that point, you don't have values. You're just like, is this polar? And then you kind of just are like, So Dr. Hernandez is all about training you guys earlier than some of the other professors, so he might wean you off the values quicker than some of the other professors might do. But some of the things you want to know about electronegativity is like carbon and sulfur, the same exact electronegativity. That is a pure covalent bond. Nitrogen and chlorine, that is another pure covalent bond. So you want to like not memorize per se, but like understand, and if that means memorize to you, you'll want to understand those values that are very similar. But if you think about it, in chemistry, we only deal with very specific elements, the carbon, sulfur, oxygen, nitrogen, fluorine, stuff like that. And so you're going to want to use your trend. And if they're far enough apart based on the trend, it's most likely polar. But what's up?
Just to be clear, on the metallic character, it increases when we go down to the left?
Yes, metallic character increases as we go down and to the left. And that makes sense because what's on the very first column, which is most to the left? Our metals, right? Our alkaline metals, and then right next to that's our alkaline earth metals. So it makes sense that we would increase to the left, and then as we go down, they just are like heavier metals, so it makes more sense that they're like more metallic in a sense. What's up?
Can you do an example of only the trends for the polar and non-polar for the ionizing?
Yes. I imagine there's one like later
Okay.
in the chapter, or in the review. Yeah, because like that's like polarity comes in the next chapter, so. I mean, and I'll be honest with you, it's more difficult than having the values. Like, I'll just be honest, it's more difficult. Yeah, but we'll talk about it. And when I say I don't think, that doesn't mean he won't put them on there. But you guys know that when he put it on there last time, it actually nullified a different question, and he had to hand out 5 points to everyone. Not that that's like a horrible thing, but he doesn't want to nullify his questions because he wanted you guys to have a specific understanding for that question, and people found a way around it, and those are the people who didn't understand it. And so he had to tell them they were right when they were wrong. Because a metalloid doesn't make an ionic bond, but based on that difference, you guys are like, technically, Dr. Hernandez, and he couldn't argue with you that you were wrong because technically you were right, but at the same time you were wrong. So what is he supposed to do, you know? All right, so calculate effective nuclear charge. So when we have effective nuclear charge, time is it, man? Okay, we got an hour. We got plenty of time. When we're talking about effective nuclear charge, we have this equation. Z effective equals Z minus S. And the very fancy way that they say this is the actual nuclear charge, and this is a charge screened by other electrons. And pretty much what it means is this is the atomic number, and this is the core electrons. That's like layman's terms for it. So if we're doing that for lithium, how many protons are in lithium? 3, right? And then how many core electrons are in lithium? 2. And then we end up with an effective nuclear charge of 1. And yeah, that's about it. So for any molecule you're asked to do this for, you would get, I mean, we have more examples right here, but you're pretty much just doing protons minus core electrons. And so if you look at a row, like carbon and silicon should have the same effective nuclear charge, right? Because when you do the math, it's like the same because they have the same amount of valence electrons. And so effective nuclear charge doesn't directly mean, oh, that's how many valence electrons. But if you look, you kind of find a trend if you do enough problems that it equals the same thing. So how many protons in magnesium? I think I heard someone say 12. And then how many of those are core electrons? 10. And so we get 2. And then for aluminum, I think it's 13, right? Yeah, 13. And then it's the same amount of core electrons, correct? Yeah? All right, cool. And so we get 3. And then sulfur, how many protons is that? 16. And are we dealing with the same amount of core electrons? Yeah, right? And so we get 6. And which one, which number is the highest? Pretty much. What's up?
The other way to do this is just follow the trend, because I know the nuclear
That's true.
charge follows more towards chlorine because atom pulls electrons in more.
Yeah.
Towards chlorine.
So that's actually a really good point. We know that effective nuclear charge increases as we go right across a period. So sulfur is the furthest right across that period, which means sulfur would have the greatest effective nuclear charge just based on the trend. So you can do the math, or you can use the trend, and you will get the same. You get the same answer. All right, cool. Thank you. Now the next question is kind of using a trend and atomic radius. So we said that atomic size increases as we go this way. So if we were looking at nitrogen and fluorine, which one of these would be larger? It would be nitrogen, right? Let's see. Yeah? Okay. It'd be nitrogen. And then when we talk about carbon, and I believe this is germanium, something like that, we would say that germanium's larger, right? Because it's below carbon. But when we do aluminum and germanium, we get something weird. This is what it looks like on your periodic table. So we would say aluminum is larger because it's more towards the left. But then we can also make an argument for germanium or GE being larger because it's more below it. And what do we say in this case? Opposing trends. Yeah, we don't really have enough information. So the key thing here is that if he says, based on the periodic trends, you don't know. I know a kid wants to memorize some of these values, and he's like, Well, based on the periodic trend, it's opposing trends, but I remember that this one was 100 picometers and this one was 150 picometers, and Dr. Hernandez was just like, I said based on the trends. You know, I didn't ask you to like memorize that, which, you know, he did awesome, but.
On the last test, as a matter of fact, they gave us the electronegativity chart, and they said, hey, for this question, you need to look at the trend, not the exact numbers.
Yeah. So like, I mean, in that case, if we let you know, do what we say, but you always look at the problem first. In the problem, it didn't say what you should use. And the reason we have to tell you guys is because you got two different answers depending on which you use. So if it's not on your test, go ahead and ask him. But if it's on your test, you want to follow that. What's up?
Can you repeat why it's opposing trends?
Yeah, for sure. So we know that the trend is like this, and it's in an increasing fashion. So pretty much that means that it increases that way and increases this way. So GE is below aluminum, which means that it's larger. Just like GE was larger than carbon because it's just below it. But aluminum is to the left of GE, and that's why we said nitrogen was larger than fluorine. So when you have pretty much one arrow saying one answer is correct and another arrow saying the other answer is correct, we don't really know because it's just a trend. It's not like, oh, you increase this much when you go to the left and this much when you go down. It's just a trend that we use. And so in this case, we don't have enough information to answer it. And so the trends kind of oppose each other. All right. So something else that came up in this chapter was electron configurations and determining whether it's diamagnetic or paramagnetic. And so for this, you really need to do like the orbital diagram for the most part. But when you're doing a cation, you should always start with what the electron configuration is for the neutral species. So you have 4s2, 3d3, right? And when we do vanadium 2+, we're going to get the same thing, except we have to take 2 electrons away. Now, we're going to want to take valence electrons away, right? Because those are the ones that are on the outside. Those are the ones that are easy to pluck off. So which one of these are the valence electrons? The 4s or the 3d? The 4s. So we're actually going to take 2 off the 4s, and what we get is argon 3d3. And then you ask yourself, is this going to be diamagnetic or paramagnetic? It's going to be para. And paramagnetic means that at least one electron is unpaired. And diamagnetic means that all electrons are paired, pretty much. Okay, so the reason I did silver, silver plus, and silver minus is this is my favorite series of electrons that you can do electron configurations for. So what you get for just silver is krypton, 5s1, 4d10. And now if we were to do silver plus, we would get krypton, and which electron would we take away? We would take away the 5s, right? So we would just be left with 4d10. And if we did silver minus, so now we don't take an electron away, we add one, where would we add it to? The 5s, right? So now we have 5s2, 4d10. So what's cool is that this one is paramagnetic, right? Because this electron would be unpaired. But both of these species are diamagnetic. And that's because now that there's nothing in that 5s orbital, all of those 4d electrons are paired. And for Ag minus, that 5s electron that was by itself is now paired. So I always think that one's cool, just because whether you take away the electron or add it, it's diamagnetic. Now, do you guys understand why this is 5s1 4d10 and not 5s2 4d9? Awesome. It's one of the exceptions. So remember, your exceptions are, and you can go find this in the book, but I'm pretty sure. So this is, oh yeah, someone has them highlighted right here, so awesome. Chromium, the one with MO, mobility, whatever, and then copper, gold, and silver. So if you want to actually see it, there's a periodic table somewhere in this chapter that shows you the electron configurations, and you can see it happening. Or you can just understand that those are the exception because you memorize it off his slides, or however you want to do it. But you have your S1D10 exceptions and your S1D5 exceptions. And those are the most important ones that he wants you to know. Okay. And pretty much I did this one because sulfur has how many electrons? 6 with a 1 in front of it. 16, right? And if we add 2 more electrons to that, we now have 18. What has 18 electrons on the periodic table? Argon. So the electron configuration for this, if we did it short, would be argon. And that's going to be diamagnetic because it's a noble gas. So something like aluminum 3+, it has 13. When you take 3 of them away, you have 10. What has 10 on the periodic table? Neon. So that's also going to be diamagnetic because it's behaving like a noble gas now. All right, cool. What's up?
I know in chapter 10 it kind of shows that that model has mostly oxygen. Oxygen is technically paramagnetic, making it align itself with the magnet.
Yeah, that's just read that chapter. I know what you're talking about. They have them between 2 poles and it's staying there. Or not that chapter, just like read that paragraph and take away from it.
I like to ask like oxygen which way would you consider it? Would it be diamagnetic or paramagnetic depending on which model?
I mean, if he said O2-, which means you have oxygen, which usually has, let's see, let's go over to it. If he said O2-, oxygen usually has 8 electrons, right? If we add 2 more, it's behaving like neon. So, I mean, if you drew out the orbital diagram for that, everything would be paired. So yeah, he's talking about, in chapter 10, there's this like paragraph or 2 that talks about how oxygen really isn't something. I would just read that and take it for what it is. Something I always say is, when something's in the book and there's like 1 paragraph on it, you just read that and that's what they want you to know about it. And everything that's above that, you'll learn at some other point. They can't teach you everything at once because then your head would just like, you just like fall down and just give up. Okay. So the most important part about this question right here and what I'm trying to say is that when we have an anion, is it larger or smaller than its corresponding neutral species? It's larger, yeah. And so that would mean that S2-, there's supposed to be a minus there, guys, would be larger. And when we're talking about a cation, is that going to be smaller or larger than its corresponding neutral species? Smaller. So calcium would be larger. And now I did this isoelectric series, which is what this is down here. All of these species have 18 electrons. But what makes them different is that they have a different amount of protons. And if we were putting these in, it says increasing order. So yeah, or like pace. I don't know how to spell. Increasing order means we're going to start with the smallest and we're going to go to the largest. So when you have, the cool thing about an isoelectric series is that your smallest one is always the cation with the largest charge, right? And your largest one is always going to be your anion with the largest charge. So it should just be Ca2+ is the smallest, then K+, then argon, then Cl-, and then S2-. Isoelectric series are like really easy actually. But the idea behind it, the concept behind it is the interaction between the amount of protons which are in the nucleus and the amount of electrons that are on the outside. So calcium has the most amount of protons, so it's going to pull those electrons in the best. Where sulfur has the least amount of protons, so it's going to be harder for it to pull in all those electrons. And that's the idea behind it. All right, ionization energies of an unknown third period element are shown below. Identify the element. So what are we looking for here? Like, what are we trying to see between the numbers? Are we looking for them to stay the same the whole time? What are we looking for? Yeah, we're looking for this huge jump. And what is that huge jump going to tell us? Yeah, it's going to tell us that we've now went from the valence electrons and we're trying to take off core electrons, which are much harder. So is this a large jump? No. Is this a large jump? Well, you have to think relative. If something's doubling, it's not that huge. And you want to look at all the numbers, really. So let's say maybe that's a large jump. And then we go from this number to this number. Is that a large jump? No, but then we go from 4,000 to like 16,000. And that's like a quadruple mint. How do you say that? That's quadrupling. So our large jump is going to be right here. And that means we have 1, 2, 3, 4 valence electrons, right? Because once we go into that huge jump, once we start using all that energy to pull off electrons, we're taking core electrons off. And so if we have 4 valence electrons, and we're in the third period, what element are we talking about? Yep. And what's up? No, what's up? How did I get 4? Okay, so. Oh, well, yeah, that's just how you know. But you want to think like relative. So if you see a jump that, and you want to kind of think of how much larger their number is getting, like compared. You don't want to like compare, because if we go from 786 to 1500, that's like a jump of 700, like relatively. But then when we go from 1500 to 3200, that's a jump of 1500. But you want to think of it from number to number. So they're both just doublings. And then when we get from this number to this number, it gets quadrupled. That number gets like humongously larger. And so we know that that's a large jump. And another thing that I've kind of noticed with these problems is like it stops right here. And usually it stops right after the big jump. So if you go look at problems in the book, there's one for aluminum. They only show you 4 values because the big jump happens at 3. And then they're like, we don't need to show you anything else because we showed you the large jump. So like worst case scenario, if you're panicking, you don't know anything, just be like, it's 1 less than the amount of values they gave me. It doesn't mean you're going to be right. Dr. Hernandez might do something crazy, but what's up?
Third period, third period means third row, right?
Yeah, so third period means third row. And groups are like this, and periods are like that. And so, yeah, it'll be scientific on the exam. All right, cool. All right, so chapter 9. Okay, so I told myself at this point I would do 1 lattice energy problem, like a Born-Haber cycle problem, if you guys wanted to do that. Do you want to do that? Yes, okay. No, I'm kidding. All right, let's work on that. So I'm going to flip to the back. All right, so we're going to do magnesium chloride. And if you guys want to do one more after this, I'll do one more. But I'm going to try to do this quick because if you've been to an SI session when we did this, it will take the rest of the time if I do it very slow. But I just want to go through it so you guys can see it. So what is the first step of the Born-Haber cycle? Sublimination, right? And so that means that we're going to go from a metal solid to, we're going to make magnesium from a solid to a gas. Okay. What will be the second step? Bond dissociation, yeah. So we're going to take this Cl2 and we're going to turn it into 2 Cls. And now, what you guys saw a lot, if you did sodium chloride, and so I'm going to like, at certain steps, I'm going to go look at other things so we can compare them because I don't want to do all of sodium chloride. That, like I said, that'll take too much time. If we did sodium chloride, so let's go up here. What is the main difference between these two and the amount of chlorines that we want? Yeah, we need 1 for sodium chloride, but we need 2 for magnesium chloride. And so the idea is when you do the bond dissociation step for sodium chloride, we only want 1 chlorine coming out the end. And so are we going to manipulate this value? Yeah, we're going to half this. But are we going to manipulate this value? No. And the idea is that you have chlorines floating around like that in the sky. And the amount of energy that it takes is to break this. And once you do that, you have a free chlorine and a free chlorine. Now, we don't half that because over here, we want both these chlorines. We half it up here because we only want 1 of the chlorines. So what's half of 2? 1. Everyone clap for themselves. So yeah, that's a big difference. And like I said, I have to show it to you because to really understand Born-Haber cycle, you have to do like 4 completely different ones and compare them constantly. All right, cool. So I'm going to box this off so it doesn't confuse us. All right, what is the third step? Ionization energy. So what is the, what kind of ion is magnesium in magnesium chloride? 2+, right? So we're going to have magnesium, which is now a gas, going to magnesium plus, and the electron's on that side, right? Because it's throwing it away. It's donating it to that pool of electrons, is the way Dr. Hernandez likes to say it. And so this would be IE1. And then we have to do it again, where we would take Mg plus, because we ionized it up here one time, and we would turn it to Mg2 plus, and thus release another electron. Any questions so far? All right, cool. What is going to be our fourth step? Yeah, we're going to ionize the anion now. And pretty much what's going to happen is the anion is going to take these electrons that were donated by the magnesium, and it's going to grab them. And so we're going to have chlorine plus an electron going to chlorine minus. And this is our electron affinity 1. Do we manipulate this step? Yes, we do, because how many chlorines do we have? 2. So we're going to have we're going to have one chlorine do this one time, and then that other chlorine is going to have to do it the other time. And if you think about it, this magnesium gives away 2 electrons, so 2 chlorines have to pick up 1 electron. And then our fifth and final step is all of this coming together, right? And this is our lattice energy step. So pretty much it's what you created. So we created an Mg2+, and I'm pretty sure on your Chapter 9 exam, the only thing he asked about Born-Haber cycle, which I know drove some of you insane because he spent so much time on it, he just asked what is the lattice energy equation for lithium oxide. And I try to tell you guys, don't get caught up on it because there's so much easier stuff to test on a chapter exam. I want to be more confident that you will get a full cycle on your final, because guess what? You have 3 hours. So you guys can sit there and stare at your page for 10 minutes and be like, oh my God, and then you can work on it for another 10 minutes and complete it. You just have more time to work out the whole cycle, to write it out and really understand what's happening. But I think if you did that on the Chapter 9 exam, most of you would have had to skip it, or you would have done it and missed a few other problems. And I think that's why he avoided it, because in the past I think that's what has happened. All right, so, and then we created 2 chlorine minuses, and they will come together to form MgCl2, which is going to be a solid. Now, there's another step, which is the formation step. And I would imagine if he asked you a question like he did on Chapter 9, like he did for the lattice energy, he would ask you about formation, because formation is a little bit more difficult to wrap your head around. And the biggest difference between a lattice energy equation and a formation equation is the fact that the lattice energy equation is the formation of your solid, your lattice structure, with what you've created. So like I said, we created this and we created this. And that's what came together to form our solid. Now, in the formation, we're going to form the exact same thing, but we're using the natural components to form it. So we would find magnesium as a solid if we went and started mining for magnesium, and we would find chlorine gas as a diatomic molecule. And they would come together to form magnesium chloride. Now I'm going to talk about sodium chloride really quick, one more time, because this is another time where we see that distinction of that half. We would find sodium as a solid, and we would find chlorine as a gas. Like, this is how you would find them. But like I said, how many chlorines do we want? 1, and we have 2. So in the formation reaction, you would see a half in front of that chlorine. All right, any questions? What's up? What's the difference between these two? Or these two? All right, so let's do it like that so we can't see. All right, so this is our lattice energy reaction, and this is our formation reaction. And the biggest difference is that when we look at lattice energy, it is what we created. It's the products of the cycle coming together to form our lattice structure. This is the favorable reaction. It's usually much more favorable. It gives us that exothermic value, where our formation is how it would come together in nature. And it's pretty much how we find these things in nature before we put them into the cycle. And so how do we find magnesium in nature? As a solid. How do we find chlorine gas in nature? As a diatomic molecule. And so you can see how this is a solid, this is a gas that's diatomic, but up here, they're both gases that are ionized. So like a really simple difference between them is in your lattice energy you have ions, and in your formation you don't. Good question. All right, I want to show one more thing and then we're moving away from lattice energy, or the Born-Haber cycle. So the hardest possible one he could give you is this right here. This is like any combination of a +2 or a +3 and a -2, or a +2 and a -3 is as hard as Born-Haber cycle gets, because you have to ionize multiple times and it's not 1-to-1. So when we talk about the sublimination step, and I honestly feel like this is what might show up on the final, guys, because he teased at it the whole time, but now on the final, like I said, you guys can stare at this and work on it for like 20, 25 minutes and still have plenty of time to get through the rest of your exam. Do I manipulate this step? I would, because how many aluminums do we have? 2. So we're going to have 2 different aluminums subliminate. And then the next step is bond dissociation. So we find oxygen in nature as O2. It's diatomic. But we want 3 oxygens, right? So how do you make 2 become 3? You multiply that by 3/2. Or 1.5 is how you'll see it on his PowerPoints. And so whatever you do to this, like however you manipulate the equation is how you manipulate the value that he'll give you on the exam. If this is how he presents it on the exam. The next step is going to be ionization energy. So we know that aluminum is going to go from aluminum to aluminum plus. I'll do it. And then it'll go from aluminum plus to aluminum 2 plus. And then it'll go from aluminum 2 plus to aluminum 3 plus. And why does this have to happen? Because we can only ionize one step at a time. Now, do I manipulate these steps at all? How many gas molecules of aluminum did we create in the first step? We created 2. So we have to do this for both aluminums. They will both have to be ionized 3 times, so we have 2 molecules of aluminum 3 plus. Now, obviously you guys can see how we would have to do something very similar for oxygen, because oxygen would go from oxygen to oxygen minus, and then it would go from oxygen minus to oxygen 2 minus. And we would have to manipulate this one 3 times, right? Or like we would have to let this happen for 3 different oxygen molecules.
So when they actually give you the actual values, do you have to then double all them and then like add it all together?
So yeah, so what Molly asks is if they give you the value, so let's say EA1 equals X and EA2 equals Y. You would have to multiply X times 3 and Y times 3, and then what I like to do is I like to add them before I plug them into that Hess's law equation at the end. Because if you don't do that for something like this, your Hess's law equation will be this long. But if you do all the math inside, like right here, then you're only plugging in one value. And your Hess's law equation looks like what you expect. It's that 1, 2, 3, 4, 5 added together equals delta H formation. Question? The way I've seen him do this problem in the past is I've seen him do this problem on the exam for calcium oxide, if that means anything to you guys. And what he did is he had these equations. So like for example, he had this equation, aluminum solid to aluminum gas, and next to it he had delta H sub equals 248. And so what you had to know about that value is that for this specific cycle, we have to multiply the number by 2. So what he did is he gave you just that equation of sublimation, but what you had to know is that it has to be manipulated, yes. And so for example, he would give you O2 to 2 O's, because if you break up an oxygen bond, you would just get the bond dissociation energy of this, you would get 1 oxygen and 1 oxygen. But you have to know that we need to multiply whatever number he gives you by 3/2 or 1.5. Now, for the bond dissociation energy, you guys saw that when I drew oxygen, there's a double bond between it. He could give you the values for everything except for bond dissociation energy and ask you to go to the table. Because what that tests is your ability to know that nitrogen has a triple bond between it, oxygen has a double bond between it, and every other diatomic molecule has a single bond between it. So, yeah. Did that answer your question? All right, cool. All right, guys. Everyone's good with that? That's like a full everything on that. Okay. Okay, so just to be honest, we have about 30 minutes left. And if you looked on the back, I have quite a bit of stuff going on for chapter 10. Do you guys want to skip chapter 9, or do you want me to try to go through all of this as fast as possible? Just, all right, raise your hand if you want me to skip chapter 9 and go straight to chapter 10. All right, raise your hand if you want me to go through this as fast as possible. Oh no, you guys lost. All right, so what I'm going to do is I'm going to go through chapter 10 in a quick manner, and then we'll come back to it. I want to do this one really quick because some of these things we'll test in chapter 10, but magnitude of lattice energy we won't see again. So at least let me do this one. So the first thing that matters in magnitude of lattice energy is charge, right? And then the next thing that matters is size. And are we looking for a larger charge? Yes. Are we looking for, and this is for a large magnitude of lattice energy. We want a larger charge and we want a smaller size. And you can refer to this right here. Q1, Q2 over R. When our charges are greater, our energy is greater. When our R is smaller, our energy is greater. It's just like we were talking about earlier with energy and wavelength and energy and frequency. You just look at the equation and if it's whatever. Okay, so the first thing I like to do is go through and give everything charges. So we have 2 plus 2 minus 2 species and 2 plus 1 minus 1 species. So right off the bat, we know that calcium oxide and strontium oxide are going to have a much larger magnitude of lattice energy. So the first thing you want to do is, it says increasing, so you would say calcium oxide and strontium oxide are going to be larger than potassium bromide and potassium chloride. So that's the first thing you want to do. Determine charge and separate. The next thing we need to do is determine size. So oxygen's not going to have an effect. What's going to have effect is calcium versus strontium. So which one is smaller? You have to know your periodic your trend and atomic radius. And so we know that calcium is going to be smaller because it is above strontium. So calcium will have the highest magnitude and then strontium. And then we talk about the plus 1 minus 1s. And we say that the difference is now the anion. So we find chlorine and we find bromine. And chlorine is above bromine, so chlorine will be smaller, therefore making it have a higher magnitude of lattice energy. And look, I set it up correctly. So there you go. Any questions about that? What is happening? Rip. What's happening? I'm freaking out. What? What is happening? Okay. No. Yes. All right, really quick, if you guys want to see that, that's what formaldehyde looks like, and that is what carbon dioxide looks like. Really quick. 5, 4, 3, 2, 1. Okay. The dots can... I can't say that out loud. Okay. Like I said, guys, these are all in the book, so you can go check them out and whatnot. But we're going to get through this chapter 10 stuff fairly quick, and I'll go back and focus on 2 of the problems that are kind of important in chapter 9. So don't stress. No stress, life. Okay, so the first one that we have to do is draw the electron molecular or determine the electron molecular geometry and the bond angles and hybridization of. So like Dr. Nana said, he can test everything, so that's kind of what I was going for. So NO3 is going to look like this. And I'm just they all have full octet. When I draw it, there's full octet. So if it has 2 bonds, you know it needs 2 lone pairs. All right, what's special about NO3 though? Does a double bond always have to be where I put it? No, it is what kind of structure? It's a resonant structure. So when we're talking about electron geometry, the only thing that matters is our electron groups. Just how many there are. When we talk about molecular geometry, we need to ask ourselves a question. Is there lone pairs? So electron geometry, we have 3 electron groups, and that means we have what kind of geometry? Trigonal planar. And then we don't have lone pairs, so our molecular geometry is going to be exactly the same, right? Yeah, okay, cool. So triplanar. And now what is our bond angles? 120. And the reason they're 120, even though there is a double bond, is because it's resonant. So the double bond is technically everywhere but nowhere. It's like, whoa, science. So this is important because if we had something like this, we would see 120 bond angles again. But if we had something like this, like the one that we just did, that I did really quick, what is the size of that bond angle? It's greater than 120 because that double bond is going to push down on the single bonds a little bit stronger. It has higher electron density. And then what is this bond angle? I did it wrong. Greater than 120, and this is going to be less than 120. No, that has to do with the fact that this double bond is fatter. It has more electron density than a single bond, so it'll push them down. Just like a lone pair would, but not as strong. All right, cool. And then what's the hybridization of all of these? sp2, right? sp2. All right, so carbon tetrachloride. You guys are going to have to keep up with me. I did not leave enough space for you guys to do this. So carbon tetrachloride, very poorly drawn, looks like this, because this is 2D pretty much. But we know that it would be that, what would be its electron and molecular geometry? Tetrahedral. So it would look like a tripod with just something sticking right out the top. If you look back there, it would look something like that if there was just a pole coming, instead of the camera, there's a pole just going straight up. If you can make it to my 2 SI sessions tomorrow, show up, because I'm going to bring the molecular kit again, and I'll try to get 2 so I can just hand them to you guys and you can mess with them and see what they look like in 3D. I've been hearing that they help. What's up? Come talk to me after. So what are the bond angles? 109.5, and what's our hybridization? sp3, awesome. So xenon tetrafluoride. So we'll have Z in the middle, or Xe in the middle. We'll have a fluoride, a fluoride, a fluoride, and a fluoride. And we have 2 extra lone pairs. And that's because, this is okay for xenon because it has an expanded octet. A few things you guys are going to want to remember is the octet rule. One of the exceptions is duet. Another exception is incomplete octet. And the last exception is expanded octet. Just go, look up those words in the index and find them and read the 1 sentence it says about it. All right, so we have 6 electron groups. So our electron geometry is going to be what? It's going to be octahedral, right? Yeah, because we have 6 electron groups. But 2 of them are lone pairs, so now our molecular geometry is going to be a little different. If you have 6 electron groups and 2 of them are lone pairs, you have a square planar structure. And what is our hybridization here? Yes, sorry, thank you. our hybridization is going to be sp3d2. The way I tell you guys to remember hybridization is the powers of these letters will equal the amount of electron groups. So s raised to the power of 1 is pretty much what we have. So 1 plus 3 plus 2 is 6. 1 plus 3 is 4. 1 plus 2 is 3. That's how I memorized it when I was in this class. And what are the bond angles? 90 degrees, yep. All right, cool. So let's do another one. I'll do one more. I'll do water. That's what water looks like in 2D. And then we ask ourselves, what's its electron geometry? Four electron groups. Tetrahedral, yeah. It's going to be tetra, and then our molecular geometry, since 2 of them are lone pairs, is going to be bent, right? And then our bond angle is going to be what? It's going to be less than 109.5. And our hybridization is going to be sp3. So remember, hybridization is determined by the amount of electron groups, just solely the number of electron groups. And that will also correlate to electron geometry. So everything that has an electron geometry of tetrahedral has an sp3 hybridization. Anything that has a trigonal planar electron geometry has an sp2 hybridization, so on and so forth. Okay, so I feel like we did a good amount of those. What's up?
Which one do you only have? There's only one I think that can have a linear. Is that trigonal bipyramidal? Is that the only one that can have a linear? Or
So that's a good question, and I wanted to talk about that. So there's 2 shapes that repeat on your table, and my favorite question to ask, and my favorite question that Dr. Hernandez asked is, your molecular geometry is bent. How many electron groups are there? Who knows the answer to that? How many? 2, no. 4, so I heard 4 and I heard 3. And let's say you can only pick one answer. The answer is you don't really know. You don't have enough information. Because if you have 4 electron groups and 2 are lone pairs, you have a bent structure. If you have 3 electron groups and 1 is a lone pair, you have a bent structure. So if he says your molecular geometry is bent, how many electron groups are there? That's not enough information. Unless one of the answers is 4 and 3. Unless he wants you to do that. But he usually asks that question and you can only pick one. And he tricks some people into picking 4 and some people pick 3. Now another way that can show up is your molecular geometry is linear. How many electron groups do you have? And that's another one, because if you have 2 electron groups, it's linear no matter what. If you have 5 electron groups and you have 3 lone pairs, you're also linear. That is a question I see very frequently. And I think it's awesome to ask, because that's just like, did you memorize the table? Something that I've been preaching at you guys for quite a while now. Let's see what time it is. Okay. So, so the reason I did both of these is because when we have BR, thank you. When we have BRF3, it looks like this. We have, it looks like this. And there's lone pairs all around the fluorines. Remember I said the way I draw it, everything has octet. I'm drawing them correctly, I promise. If you don't believe me, go look in the book. And then if I'm wrong, you can make fun of me later. And so how many electron groups are there? 5. So our electron geometry is going to be trigonal bipyramidal. I am a science major, everyone. And so the way I remember 5 electron groups is tri equals 3, bi equals 2, and that's 5 together. So that's how I like to remember that. It's really easy. Once you guys look at the table, some of them are extremely straightforward and they make sense, and some of them are like, what was this guy thinking when he made them? So some of them are really straightforward. What's going to be our molecular geometry? So we have 5 electron groups and 2 lone pairs. T-shaped, yeah. And then what's our hybridization? Yeah, because like I said, 1 plus 3 plus 1 should equal 5, and that's how many electron groups we have. And then bond angles for this, I gotta look this one up. I don't even memorize it. Does anybody know? Less than 90? I'm gonna have to believe you, man. I think he's right though. Yes, it is less than 90. I think the 5 electron group part of the chart is the hardest part to memorize. Like, honestly. Like you said, I'm naming out all the other ones, but when we started talking about this, I was like, I don't know. Okay, so the reason I did BRF3 and BF3 is because this is what BF3 looks like. And some of you are like, what the heck? B doesn't have its octet filled. B boron is an exception to the octet rule. It has an incomplete octet. 6 electrons fills its octet. So this is how it looks, and it's very satisfied. And then so we have trigonal planar electron and molecular geometry. We have sp2 hybridization, and we have 120-degree bond angles. The reason I'm not writing this is because we've done trigonal planar like 4 or 5 times already.
Do you think we're gonna get any of like these CH?
Oh yeah, of course. It's the final exam. Why not?
Can we go over them?
See, okay, so that kid left. He was in Dr. Patino's class. Dr. Patino is like doing like the first chapter of organic. Like he goes, some of these professors go deep into organic, and so you would have to know how they're named. And Dr. Hernandez says you don't need to know how they're named. You just, if I give you the chemical formula, you need to know how to draw it. And so we've been doing stuff like CH2O, which is formaldehyde, which is C double bond O with 2 H's. That's an organic compound, but it's really it's like simple. Now I put these in there because, and you see they're starred. The starred ones are organic compounds that you need to know how to draw it, but you don't need to know how to name it. And so I think it's important that, you know, I at least put them forward for you guys. But pretty much for this one, it would look like this, right? Can you guys see it? CH3 COOH. And some of you are like, how would I know how to do that? How can I do that as fast as you just did it? You can't. There's no way you can do it as fast as I just did it because you don't know it like that. So you'll have to do trial and error. And you'll have to make mistakes. And then you'll have to be like, oh man, this is what it really looks like. Remember what I said, the determining factor is going to be formal charge. So formal charge is absolutely 100% reduced in the structure. There's not a formal charge anywhere on this structure. And if you drew it any other way, you would find at least a -1 or a +1 or something like that. And then so just to continue with what we've been doing, if we look at this one right here, what is its molecular and electron geometry? Tetrahedral. And what is its hybridization? sp3. This one right here, it has 3 electron groups. So what's its molecular and electron geometry? Trigonal planar. And its hybridization is going to be sp2. And this one right here, it has an electron geometry of tetrahedral, but it has a molecular geometry of bent. So its hybridization is going to correspond to its electron geometry, which will be tetrahedral again.
So you split them up by the center.
Yeah, when we're talking about stuff like that, we want to look at the central atom and what it's connected to. So, yeah. Okay, I'll do one more of these. I'll do this one right here because this one's kind of weird. But it'll be C. What's up? Talk to me.
Say one more time the structure for that one, that last one.
This one right here?
Yeah.
We would have tetrahedral, sp3, trigonal planar, sp2. Molecular geometry of this would be bent, but its hybridization is still sp3. No worries, no worries. All right, so this one right here would look like this. Yeah, that's what it looks like. And so same exact thing, you know what I mean? Like we would have the sp2 trigonal planar and the sp3 tetrahedral. It's just a little bit different, but pretty much it has components of the last structure we just drew. Okay, so let's talk about polarity really quick because I know most of you are worried about polarity. Right here, we have polar bonds, but it's a linear structure, so the polarity cancels out, right? So CO2 is not polar. What? No? Okay, cool. When we have H2O, now remember, I drew it 2D last time, and now when we're talking about polarity, we need to try our best to draw it 3D so we can look at it in a 3D sense. H2O has polarity going this way, and it would have a huge dipole going that way. So this is yes. Now if you looked at this, I got your question, one second. If you looked at this like it was in 2D, how I drew it before, you would probably say, hey, the polarities cancel out. So you got to make sure you look at it in 3D. Question?
Do we need numbers, or is it just yes or no?
Okay, so if he gives you the numbers, you're going to want to use them. You're going to want to do what will be 3.5 minus 2.5, and you would get 1, and so you know that's polar, and then so you would know the polarity goes this way. Same thing for this one. Oxygen is 3.5, hydrogen is 2.1, so you would know that the polarity goes towards oxygen. Now, if he doesn't give you your values, you would know that electronegativity increases going this way. So C is far away enough from O for you to say that it's polar. Now, going back to her question earlier, she was like, can you do one? Show us how to find polarity just based on the trend. That's how you would have to do it. As you move more towards the right and as you go up, your electronegativity is increasing. And so we see that oxygen and hydrogen, oxygen's, it's over here, it's off the page, but there's polarity between that.
So with CO2, the bonds are polar, so it makes more molecules.
Yes, that's a good question. So with CO2, we have polarity along the bonds, but in the molecule we don't, because it cancels out. And I'll be honest with you guys, at your level, it is difficult to understand, because there's so many weird things happening with electronegativity, it will be more difficult just to use the trend. You will run into weird spots, but I imagine if Dr. Hernandez is not going to give you the values, he's not going to make your life horrible about it. Like, he'll give you things that if you use a trend, you won't run into weird situations. But like I said, you want to know things like carbon and sulfur have the same electronegativity. So when they make a bond, it's pure covalent. Nitrogen and chlorine, they make pure covalent bonds. I think oxygen and iodine have similar polarities and stuff like that. The only reason I rattle off numbers is because my Bio 1 professor made me memorize it a long time ago, and I just never forgot it. So don't get intimidated by the fact that I know it, because you don't have to memorize the values. I just have them in the back of my head. So I would say just try your best to use the trend if you don't get the values, and if you get the values, use the values. Like, if you don't know, just use the values every time. But since you see that a carbon-oxygen bond is polar, anytime you see a carbon-oxygen bond, it's going to be polar. Like if we look over here, if we just had this structure right here, we know that this is polar. So if there was an H right there in that formaldehyde that we did, we know that this is a polar molecule because there's polarity going that way. And so just try to get used to some of those things just in case. But I don't really know, because we haven't talked about it, and I don't know what he's going to do. Okay, NH3, we have to think about it in 3D. And there's going to be a lone pair, so these are going to get pushed down, so you're going to have polarities going that way. And what you're going to get is they kind of add up to this net dipole that does that. Yes. CF4. Now what you'll have is you'll have something that kind of looks like this. This one is kind of deceiving even in 3D. If you draw it on a 2D surface in 3D, it's still kind of deceiving. But if you've been to SI and you've seen me push over a tetrahedral molecule, it looks the same every time I push it over. And that's because these bond angles are 109, right? 109.5, they're all equidistant. So carbon-fluorine bond is polar. But it's equal, all the bonds are equally polar, pulling in opposite directions. So they're all pulling in equal but opposite directions. Meaning equal in terms of strength, but opposite in terms of it's equidistant. So there is polarity in the bond, there is not polarity in the molecule. And the reason I added this one down here is because we would see C bonded to an F, bonded to an F, bonded to an H, bonded to an H. Now what will happen is, well, first of all, is a carbon-hydrogen bond polar? No. Thank you. Carbon-hydrogen bond is not polar. There's no polarity there. So these bonds are polar, and what they will do is, since there's nothing to counteract them like there was over here, they will just add sort of in this direction, and you'll see a net dipole. Yeah. So just try your best when it comes to polarity. I hope, I would like to be confident and say that he'll give you some common molecules that you should be comfortable with their polarity. Things like, look in the textbook, like things like NH3. You should understand that nitrogen and hydrogen have a polar bond. Fluorine, it doesn't matter what fluorine is with. If fluorine is with a non-metal, it's a polar bond. If it's with a metal, it's an ionic bond. Fluorine never forms a non-polar bond. Okay, so I have, oh yeah, I'm sorry. This is not polar and this is polar. Thank you. Okay, guys. All right. I'm gonna do this one really quick, and then I'll do the bond energy really quick, and then I gotta go because I'm supposed to be. Oh, okay. Yeah, I didn't even. Okay, I have the orbital theory. Do you guys want me to do this orbital theory? Yes. Oh my God, yes, please. All right, so you guys have not learned this yet in class, so you have to take that into consideration. That's why it seems crazy. He said, "Please show up to class." Please, like he was like, "Please show up to class." That's because this is what he's gonna blaze through tomorrow, and then he's probably gonna do some questions that you're gonna want to take home from his class. He'll probably do some high-level questions from all the chapters that you'll want to take notes on and keep in your book. All right, so the idea is when we're doing this kind of problem, something that's very important is, and so the other two problems that I said I was going to do, they're examples from the book. So you can go see how they're done. And like I said, even if you haven't come all semester, please try to show up to my SI sessions tomorrow. I have 2 more. That's the last sort of help I can give you guys for the rest of the semester. And I'll do my best to get through as much stuff as possible. It'll literally be 2 more hours, and they're back-to-back. Show up to whichever one you can show up to. Bring your questions. If you show up before me, write them on the board. That way I can start the second I get in. All right, so when we're talking about molecular orbital theory, which, like I said, he'll talk about more tomorrow. He'll give you the details about it tomorrow. There's about 3 to 4 pages of just words on this. You got to read them, because that means he'll pull some concepts out of it and test you on them. All right, so when we're doing this hydrogen, this H2 minus one, pretty much what's happening is you have your 1s sigma bonding and your 1s sigma non-bonding. And you guys just kind of got to keep up with me. You really don't know what's happening because it has not been taught to you yet. So what happens is, for you to have H2 minus, you have to have 2 hydrogens, and one of them has to donate like a negative charge. But an easy way I like to look at it is we say, how many electrons would be in an H2 molecule? 2, right? And then if we added a negative to that, that means we have 1 more or we lost 1. We have 1 more. So there's 3 electrons. So you would say 1, 2, 3. You just count. You start from the bottom and you fill up the boxes until you run out of them. And you always start from the bottom and you always move up. Now, the equation is going to be bonding minus non-bonding. Am I off the page? Oh, no. Divided by 2. So in this case, it's going to be 2 minus 1 divided by 2. And that's going to give us plus 1/2, right? Now, what they ask you is the H2 bond stronger or weaker? Is the H2 minus bond stronger or weaker than just an H2 bond? Now, if we just did H2, we would only have 2 electrons. So we would only fill up this box, right? And so what we would get is 2 minus 0 divided by 2. So what you would have for H2, you would have 1. And for H2 minus, you would have 1/2. Which number is larger? 1. So 1 is a stronger bond order. It'll form a stronger bond. All right. I'm going to do this one and then we're out. So when it comes to second period molecules, you have to consider a chart that's on, it's like on page 465, probably 468 if you have 4th edition. And for boron, carbon, and nitrogen, the way that the orbitals fill up, it goes pi sigma, pi sigma. And you guys probably are like, what the hell are you talking about? For oxygen, fluorine, and neon, it goes sigma pi, pi sigma. And that's just something that you'll have to memorize. And the way I say to memorize it is that division happens right here, and the second group starts with oxygen, and they go sigma pi, pi sigma. So oxygen is a circle, sigma looks like a circle. That's how I memorize it. If this is like going straight over your head, you're going to want to try to show up tomorrow. And if you can't, I'm really sorry. So the way we draw it is sigma 2s, sigma anti-bonding 2s. And then, oh, okay, thank you guys. And then from that we do, since it's nitrogen, for nitrogen we go pi, sigma, pi, sigma. And these are anti-bonding. And so in an N2 molecule, how many electrons do we have? Valence electrons. We have 10, right? And if we have a negative sign, now we have 11. So what we do is we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And what we get is 8 minus 3, because these 3 are our bonding, and these 2 are our anti-bonding. And then we would divide that, and we would get 2.5. Now it asks you, let's go to the third question first. Is N2 minus diamagnetic or paramagnetic? Do you see any electrons that are unpaired? Yeah. Yes, so that means it's paramagnetic, right? And then it says compare it to an N2 molecule. So like I said, N2 would just be 10. So we would have everything the same except for that electron right there. So we would get 8 minus 2 divided by 2, and that would be 3. So this is N2. This is N2 minus. Which number is bigger? 3. So N2 would form a stronger bond. Say that question one more time. No, yeah, when it's not making an ion. So how we find it in nature is stronger than if we added an electron to it. Question? I believe it has to do with whichever one has a higher electronegativity, but you're going to want to read the book about it. And that'll be explained in the book, and please show up to class because he'll most likely say it tomorrow. Question? My SI sessions tomorrow at 12:30 in TA 202B and 2 o'clock in TA 116. All right, guys, thanks so much for showing up.